Hello and welcome to today's webinar. Put it on the first. My colleague Dr. Qian Zhu will present today on the subject of her latest report, which is the developments in circulating fluidised bed combustion. If you have any questions, do ask them by clicking on the question button at the top of your screen, and Qian will then answer your questions at the end. The slides will be available from the webinar page of our website later on today if you wish to download them. And also, can I remind you that if you are a resident in a member country or an employee of a sponsoring organisation, you can complete the registration form on the bookshop of our website and then download our reports at no charge. Okay, Qian, over to you.
Good afternoon, everybody. Today I'm going to present to you my latest work on developments in circulating fluidised bed combustion. As an alternative to pulverized coal combustion for power generation, CFBC technology offers several benefits. CFBC boilers are extremely flexible, allowing a wide range of fuel qualities and sizes to be burned. CFBC boilers have low emissions of SO2 and NOx, without addition of expensive flue gas emission control systems due to the in-furnace desulfurization and the relatively low combustion temperature. CFBC systems have good combustion efficiency and provide operational flexibility. The current status of the technology is such. A vast majority of existing CFBC units are subcritical with single reheat that can achieve a plant efficiency of between 38% and 40% based on low heating values. Higher efficiency can be achieved by the emerging subcritical larger CFBC boilers. The world's first supercritical CFBC plant with a capacity of 460 megawatts electric has achieved a plant efficiency of 41.6%. It is claimed that modern CFBC power plants can achieve a net plant efficiency of up to 45%. CFBC boiler can achieve the average availability of 90% or higher. It can operate at base load or in a load following mode, but it is not suited for on-off cycling. CFBC boilers are capable of burning all types of coals, coal waste, and a wide variety of bituminous biomass and waste-derived fuels, alternatively or simultaneously. And a wide variety of opportunity fuels can be used almost interchangeable without major, if any, plant modifications. A modern CFBC plant can achieve an in-bed sulfur removal efficiency of 95%, and the emissions of NOx and the particulates is less than 250 milligrams per cubic meters, respectively. Recent CFBC units have used post-combustion controls such as the dry scrubbers or SNCR to further reduce emissions of SO2 and NOx to meet the increasingly stringent emission requirements. Almost all the existing CFBC installations in operation are subcritical, but supercritical or even ultra-supercritical CFBC boilers are not commercially available. The largest CFBC unit in operation today is the 460 megawatt bituminous coal-fired CFBC plant in Poland. More larger CFBC boilers are being commissioned or under construction, which I will talk about in more detail later in this presentation. More than 600 coal-fired CFBC power generating units with a total capacity of over 46 gigawatts are in operation worldwide, and nearly 180 units with a total capacity of over 26 gigawatts currently are under construction or planned to be built. The design of the furnace is key to successful and efficient operation of a CFBC boiler. The nature of CFBC combustion poses a limitation to furnace dimensions. Different approaches are taken to overcome this when scaling up. Alstom has adopted the pump-leg design in which the lower furnace hopper is split. Each hopper is equipped with separate fuel and air feeding systems. For Wheeler CFBC furnace, however, has one single fluidizing grate under which there are several separate air plenums introducing primary air to furnace. The primary airflow through the air plenum is individually measured and controlled to ensure equal airflow to all sections of the grate and the uniform fluidization. One of the key components in the CFBC boiler is the solid separation system. Two main types of separators have been applied in commercial CFBC installations. They are cyclones and the impact separators. Cyclones are the most commonly used. With the development of water or steam-cooled cyclones, the plant availability is significantly increased, where the maintenance and operating costs are considerably reduced. This figure shows the compact separator design introduced by Wheeler that uses pentagonal-shaped membrane water walls with a thin layer of refractory inside the separator to smooth out the corners and has a smaller footprint. For smaller CFBC boilers, impact separators such as the Babcock-Wilcox two-stage solid separation system are used. Several other cyclones with novel designs are under development at the moment. For scaling up, cyclones of a proven size and design with the optimal arrangement of the cyclones are used. And this figure just shows the principle of the cyclone arrangement for scale up. For large CFBC boilers with reheat, it may not be possible to perform all the required heat duty in the furnace and the backpass, so external heat exchangers are needed. Bubbling fluidized beds are normally used to extract heat from the hot circulating solids collected by the cyclones. The major advantages of using an external heat exchanger are its ability to adjust the superheat and reheat steam temperature and to control the combustion temperature. This figure shows an integrated recycle heat exchanger developed by Wheeler. Old-time CFBC boiler usually features pant-like design with EHEs on each leg. Over the last 10 years, one of the significant advances in CFBC technology has been the increase in capacity of CFBC boilers. Early CFBC units are mostly 30 to 50 megawatts in size, and over the years, capacity of CFBC units have increased. This figure shows India's experience with CFBC boilers, and the increase in CFBC boiler capacity over the years is clear to see from this figure. As shown in this figure, a number of CFBC units installed since late 1990s are in the range of 250 to 330 megawatts in size. As mentioned earlier, the largest CFBC unit in operation is a 460 megawatts CFBC boiler at Lasna power plant in Poland, which started operation in 2009. Recently, Korean Southern Power Company KOSPO has chosen Foswheeler to supply full 550 megawatts supercritical CFBC boiler to its Samchok power plant. These units will fire bituminous coal and biomass fuel and are scheduled to start operation from 2015. And currently, a 600 megawatts supercritical CFBC demonstration unit is under commissioning at coal-fired biomass power plant in China. This is domestically designed and manufactured by Chinese company, and it uses Alstom's pant-like design. Once in operation, it will be the world's largest CFBC boiler. Today, CFBC boiler with capacity of up to 800 megawatts is commercially available. Further scale-up of CFBC units to above 800 is possible. To move CFBC technology to advanced steam cycle conditions, Alstom and Foswheeler have both adopted one-throw boiler technology in their design of super CFBC boilers. And here are the steam conditions used by the recent supercritical CFBC boilers. It is anticipated that future CFBC power plants will routinely use advanced steam parameters. Apart from the technological advances we just discussed, developments have also been made in other parts of the CFBC system. Various forms of bottom ash cooling have been developed, and work to improve the design of the ash cooler is continuing. Here are examples of some of the fluidized bed ash cooler designs. Also, improvements in refractory system designs, fuel and solvent feed system design, and the ash extraction equipment design have been made that address the initial problems encountered with these system components. Furthermore, modifications and optimizations in the design and the operating parameters of CFBC boilers have led to successful operation of a large number of CFBC plants that coal-fire coal and biomass or waste-derived fuels. Oxy-fuel combustion is one of the main options for CO2 capture from combustion plants. This figure shows a simplified process flow of the Oxy-CFB combustion plant. It consists of the air separation unit, an Oxy-CFB power generating plant, and a CO2 treatment unit. In principle, normal CFBC boiler designs with reasonable modification can be applied for Oxy-CFB boilers. However, there are several challenges in designing Oxy-CFB boilers. For example, in oxygen combustion, the flue gas volume flow decreases considerably, resulting in significant size reduction in the furnace, cyclone, convection path, and other equipment, as illustrated here. On the other hand, increasing oxygen content leads to higher combustion temperature, which will increase the need of heat transfer in the furnace and its share of the overall boiler heat duty. This creates a challenge to manage the furnace temperature levels and to locate and develop designs for heat exchanges in the hot loop of the Oxy-CFB boiler. There are several facilities from laboratory to pilot scale, primarily in research centers and universities around the world that are engaged in R&D on oxy-fuel combustion technology. Some of them are listed here. These facilities are mainly used for fundamental study in various aspects of oxy-fuel combustion. Currently, the CIUDEN R&D demonstration project is being actively pursued. Its objectives are to validate the full chain of CCS technologies and to acquire data for scaling up both the Oxy-PC and the Oxy-CFB units. CIUDEN Technology Development Center has a 30 megawatt thermal Oxy-CFB boiler. The main components of this boiler are shown here. The main focus of the project is to support and validate the scale-up of Foswheeler's flexi-burn CFB technology, which will be the basis for a 300 megawatts Oxy-CFB project, which is called Compostilla Oxy-CFB 300 project. The CIUDEN CFB unit was commissioned in September 2011. Tests have been carried out since then. The power output of the Oxy-CFB unit will be lower compared with the corresponding air-firing CFB unit due to the additional power consumption by the air separation and the CO2 processing units. In general, the efficiency penalty is about 10 percentage points in Oxy-CFB operation compared to air-firing. In terms of operation, bad agglomeration is not a major issue for a properly designed Oxy-CFB boiler. No significant changes seem to occur in emission levels of SO2 or NOx, and the emissions of other pollutants are comparable to those with air firing. The total plant cost of the Oxy-CFB plant are higher due to the relatively costly and the power-consuming air separation and the flue gas treatment system. An Oxy-CFB system has all the advantages of the CFBC technology and has some additional advantages over Oxy-PC. The combustion temperature in the Oxy-CFB boiler can be controlled by the cooled circulating solids, so the flue gas recirculation rate is minimal. Reduction in flue gas recycling leads to reduced size of the boiler island and some of the power consumption, potentially allowing more compact and less expensive Oxy-CFB boiler. Transition from air to oxygen combustion is potentially easier relative to Oxy-PC because Oxy-CFB has large amount of inert bed material that also helps in controlling the bed temperature. Oxy-CFBs do not need new sophisticated burner design and management, so it is easier to implement. The strong mixing in the Oxy-CFB furnace and the long residence time due to the recirculation of solids allow a good carbon burnout, and this clearly suits the low reactive fuels. Large part of the Oxy-CFB furnace operates at positive pressure, so the air in leakage is low, and it uses low excess oxygen, resulting in increased CO2 recovery and a reduced energy penalty. In conclusion, CFBC technology has advanced significantly in recent years, making it a real competitor for coal-fired power generation. The Oxy-CFB technology is developing rapidly and will continue to evolve. It is expected that we'll see more increased application of CFBC technology in the power generation industry in the near future. Thank you very much for your listening.
Thank you very much, Qian. We're now going to see what questions have been submitted, and while I'm looking through these, of course, there's plenty of time for other listeners to submit more questions. Okay, Qian, the first question is, a PC boiler can have a size of up to 1,300 megawatts. How can a CFBC boiler compete with this?
Well, the CFBC boiler can have a size up to 800 megawatts now, and it's still flexible. Depends on the local conditions. If only the low-grade fuel is available, and especially when there are some opportunity fuels, such as seasonal agriculture waste, is available, then the CFBC technology is very suited for that situation.
Thank you. Another question has come in. Qian, you showed the emission levels of a CFBC boiler, and they're not that impressive. Much lower emissions can be achieved today by a PC plant. Is this likely to limit applicability of CFBCs as legislation tightens in the future?
The CFBC boiler at the moment, without any addition of flue gas treatment systems, can meet the emission requirement in most regions. However, you can use the post-combustion systems, such as the dry scrubbers or the NCR system, to further reduce its emissions.
Thank you. And the next question, can you quantify the minimal levels for excess oxygen and air ingress for Oxy-PC and Oxy-CFB?
For the Oxy-CFB, the air in leakage rate is potentially 1%, where the Oxy-PC is possibly 5%. For the air excess oxygen, I don't have the figure right now, but I can email you if I can find it in my report.
That's a good point. If you have more questions, do email them to Qian or add your email address to the questions you're typing in, and she'll be able to get back to you with a fuller answer. Okay, the next question. Do you have any comment to make on SO3 emission from Oxy-CFB boilers?
No. I'm not. I don't have much information on this, but I can do a research afterwards. If I come up with any comments, could you just give me your email address? I can contact you later.
Thank you. There's 4 more questions. The emission reduction is excellent as far as SO2 is concerned. What about the rate of N2O, which is still high compared to PC technology? Have you considered that, Qian?
Well, this is one of the shortcomings of the CFBC technology.
Do you think the share of CFBC boilers will overtake PC boilers in power generation applications in the future?
No, I don't think so. Not in the near future, but you will see increased application of CFBC in the near future, especially in some regions.
Another one about Oxy. Why does Oxy-CFBC have a better size reduction advantage than Oxy-PC? Is this due to it being able to increase solids recycle?
Yes, because the temperature can be controlled by circulating of the cooled solids, so the flue gas recycling rate is much lower than Oxy-PC. That's why it has a smaller size.
And the final one, which is not a question, but to support your comment on CFBC. It is being the boiler of choice for some African countries because of the fuel feed being low grade and often byproduct from a coal preparation plant that would otherwise be used as backfill in mining, but it still has a useful heating value. So thank you very much for that comment and for all the questions. As we don't have any more, I'll just thank Qian on your behalf and tell you that the next IA Clean Coal Centre webinar will be given by Colin Henderson on the 12th of June at midday UK time. His subject will be on upgrading and efficiency improvements of coal-fired power plants. So thank you all for listening. Bye-bye.